everyone. Today we are going to discuss applications to whatever we know about nonlinear systems to populational biology, section 6.3. I'm going to take some particular biological model and try to study its equilibriums. So I choose the model of competing species, so let X and Y be the amount of some animals, species that compete. First of all, you write out the logistic equation on X. It is here in red. This is logistic growth, so the populational growth will slow down as X increases, and you do same for Y. And now you add terms that show that your species compete. So these nonlinear terms are over here. They show that X species is harmed by the fact that Y species is present. The more Y is, the more this negative term is, and same here. So species are harmed by their coexistence. I'll rewrite these equations in the following way. So when X is absent, then you only have, if X is 0, you only have the logistic equation on Y, and same for X. And we are going to assume that all coefficients are positive, and X and Y are also positive, non-negative. Sorry, this should be non-negative, because X and Y is the amount of animals. We are going to study equilibriums of this system using linearizations, as we discussed on the previous lecture. So first of all, let's find equilibriums. Equilibriums should be zeros of the right-hand side. So either X and Y are both 0, or X is 0 and this bracket is 0, or Y is 0 and this bracket is 0, or both brackets are 0. We have 4 possibilities. This gives you 4 equilibriums. 0 equilibrium corresponds to the case when you have no animals at all, and this is not going to change. The second equilibrium is when you have no X species, and then Y is at equilibrium position for the logistic equation. Same for this equilibrium. And then the most interesting equilibrium is when both X and Y are non-zero. This is when species coexist. The amount of both organisms are both species are non-zero. Let's take some particular case and study it using our methods. So this is some particular equation. I fixed some values of constants, and I made a picture of the corresponding vector field. At each point I draw this vector, and I also draw black dots where the vectors are 0, which means that the right hand side is 0. These are points for equilibriums. We have 4 equilibriums. To study equilibriums, I will need to compute the Jacobian matrix. So its rows are partial derivatives of the first equation, X derivative and Y derivative, and partial derivative of the second equation. This is X derivative and Y derivative. This is not prime, this is comma, I'm sorry. Now we have 4 equilibriums for the system, and we are going to write out the linearizations. The matrix of linearization is equal to the value of G at the corresponding point. So the linearization at 0, 0 will be, you just substitute 0 in this matrix and you get 1, 0, 0, 1. So the linearization at this point is a linear system with this matrix. This is a nodal source, because both eigenvalues are positive, which means that the nonlinear system also has a source. Theoretically, it could be a spiral source, because eigenvalues are equal here. But there is no space for spiral in here, because the vectors are horizontal on this line and vertical on this line. There will be no spiral, there will be just a nonlinear node here. This is 0, 0 equilibrium. Well, this is good, because when you have small amount of both kinds of animals, this amount will increase. You will go away from this equilibrium. So it's good that this point is a source. Now let's take the second point at 1, 0. It is over here. I substitute 1, 0 here, and I get that this linear system has a nodal sink at this point, because you have the negative eigenvalues. This is a sink. So the nonlinear system also has a sink. And same for 0, 1. This is the matrix. Eigenvalues are -1. The linear system has a sink, so the nonlinear system has a sink. You may also say that it could have a spiral sink because eigenvalues are equal, but there is no space for spiraling because vectors are vertical along this line, so this will be a node as well. And now comes the most interesting point. This point over here, 1/7, 3/7. I just solved this system. This and this should be 0. I found this point where these expressions are both 0. It is 1/7 and 3/7. And substituted these numbers in the Jacobian. That's the matrix I got. Then I found its eigenvalues. They happen to be real and different signs, which means that this point is a saddle. This point is a linear saddle for a linearization, so the nonlinear system also has a saddle over here. So source, node sink, node sink, and a saddle. And now I can show you the phase portrait. Here it is. So you can try to draw the lines that are tangent to all the vectors. So they will be phase lines, but it is difficult to draw them, especially near this point, unless you know that this point is going to be a saddle. But I know that it is going to be a saddle, so I just draw a saddle here, and now it is more or less simple to draw vectors that are tangent to all the vectors. That's the picture. That's the phase portrait. Now let's figure out what does it mean for the system. If you start at some initial amount of animals, like say here, then you can follow the phase curve and see where it gets. This phase curve gets to this equilibrium, which means that y tends to 0. Y species dies out. Along this phase curve, the y species died out. When you start here, then you follow the phase curve to get to this equilibrium, and then x species dies out because x tends to 0. You can try to start here, then you still tend to this equilibrium, or if you start here you tend to this equilibrium. Some of the species will die out. This is an unpleasant picture for both species. They cannot coexist. Whenever you start on the picture, you will tend to either here, or to either of the stable equilibriums, and so this means that one of the species dies out. There is one, or actually two, exceptional phase curves. They are separate traces of this saddle, this line. When you start here, it looks like you can tend to this unstable equilibrium, and it seems like species can coexist, because x and y will tend to some non-zero value. But this is not right, because if anything happens to your animals when you follow this trajectory, then you move either this way or this way. Random perturbations always happen, and then you tend either to this equilibrium or you tend to this equilibrium. So this picture shows that the species just cannot coexist peacefully. Even these trajectories that are mathematically possible are not actually biologically possible, because any random perturbation will take you away from them, and then one of the species dies out. This is an unpleasant picture for the animals. On the next slide, I will change these coefficients and show you a better picture. So let's have a little break now.